Chapter 1, Lesson 1 of Geometry, the first lesson of the year. We're going to look at patterns and inductive reasoning. Okay, and how do we use inductive reasoning? What is it, and then how do we use it? Okay, so let's go ahead and we're going to take a look at a few vocabulary words first. And again, we talked about how you take notes. We're going to look at the paragraphs in the book. We're going to look at what the main points are. We're going to write those down. We don't want to copy the book. Okay, that takes a long time. It's a lot more to memorize if you're trying to memorize every single word that somebody else wrote in the book. And quite frankly, it's really unnecessary. If we needed another copy of the book, we'd just go buy another copy at the store or get one from the publisher or make a copy on the copy machine. So taking the time to copy by hand what's in the textbook onto your notebook paper in your notebook is really doesn't make much sense at all. Again, if we needed a copy of it, we just go buy one. What you're looking for are just the key points. What are just the main points of what's being talked about? And that's what you're looking for when you're reading the paragraph. So let's take a look at the first paragraph. Inductive reasoning is reasoning that is based upon patterns you observe. If you observe a pattern in a sequence, you use inductive reasoning to tell what the next term in the sequence will be. So we look at inductive reasoning, and most students would just copy this down right here and then call that the definition of inductive reasoning. The problem with that is that the paragraph goes on to explain some more things about inductive reasoning, and that's what most students miss. Okay, so again, we want to read it. We want to look at the key points. Go ahead and we'll highlight them. I'll highlight them on the board here, and then we're just going to write those in our notes because it'll be easier to memorize and you'll get just the main points. So as I read this, inductive reasoning is reasoning based upon patterns. So the first thing I realize, or I see, that it's based upon patterns. If you observe a sequence and pattern, you use inductive reasoning to tell what the next term in the sequence will be. So what do I use? I use inductive reasoning. I look at the patterns to figure out what the next term will be. And really, that's all the information that I need. So when I'm writing in my notes, okay, I want to write down the topic that I'm looking at. In this term, in this case, excuse me, it happens to be a vocabulary word. What is it? It's an observed pattern. Something I look at is a pattern that I observe. What do I use it for? To get the next term in the sequence. Okay, so, and then I might want to put an example. So here I have example 1, 2, 3. What would be the next term in the sequence? Based upon what I see, 1, 2, 3, I would guess that the next term is going to be a 4. The pattern seems to be that the numbers are going up sequentially, so the next number would be a number 4. So I used inductive reasoning to look at a series and to make a guess about, excuse me, to make a guess about what the next number might be in the sequence. That's inductive reasoning. So again, I don't need to copy the whole paragraph. I just need to know that it's patterns that I look at, and then I try to figure out what the next term is. That's all you need to have in your notes. All that other stuff is not necessary. Okay, let's look at another word, or the next paragraph. A conclusion you reach using inductive reasoning is called a conjecture. So here's another word, and again, as I read this, I don't want to copy this whole thing down because then I'm just going to have to memorize all of that. Just what's the key point? What is a conjecture? It's a conclusion. Okay, it's a conclusion that I get that I used inductive reasoning in order to get it. So, and again, in my notes, the term I'm talking about is a conjecture. It's a conclusion. Okay, and how did I arrive at the conclusion using inductive reasoning? That's really all it is. A conjecture is a conclusion. Okay, now, if you memorize this, then you can fill in the rest when you have to write it out for yourself. What's a conclusion? Okay, conclusion reached based upon the patterns that I looked at. Okay, so 1, 2, 3, what would be the conclusion? My conclusion would be 4. So based upon the pattern that I see, I think the next number is going to be a 4. Okay? All right, next paragraph. Not all conjectures turn out to be true. In other words, I might look at a pattern and think it's one thing, but that's not true. Well, how do we know it's not true? It says you can prove that a conjecture is false by finding one counterexample. A counterexample to a conjecture is an example for which the conjecture is incorrect. So what are the key points there that I want to look at? Okay, how a counterexample. What is a counterexample? It's an example for which the conjecture is incorrect. It shows that the conjecture of someone else is wrong. In other words, you arrive at a different conclusion using the exact same pattern. Therefore, their conjecture is false. Now, if they can provide a counterexample for yours, yours would be false. Okay? And it's how you prove a conjecture is false. Okay? So you can't just say, hey, you're wrong, you're wrong. You have to give an example. Okay? Again, it's one of the things about geometry. It's not enough just to say, well, because. You have to be able to provide an example. So, in our notes, we might write something like this. What's a counterexample? It proves a conjecture false. You have to provide an example. Again, it's not enough to say you're wrong, you're wrong, you're wrong, no, you're wrong, you're wrong, you're wrong, which is what I hear all the time. Okay, you have to actually give an example where you show that the person is actually wrong in that conjecture. So let's go ahead and use inductive reasoning for some homework problems. Okay, it says find a pattern for each sequence and then use the pattern to show the next two terms. In other words, we want you to use inductive reasoning. We want you to look at the pattern and take a guess or make a conjecture about what do you think the next two numbers will be. So here we have 5, 10, 20, 40. So what do you think the next two numbers will be? Well, I have to look at the pattern. So how do I get from 5 to 10 and then from 10 to 20 and then 20 to 40? What's happening in each step of the sequence? Well, it looks like here, if I take 5 and multiply by 2, that gives me my 10. Then if I multiply that by 2, that gives me my 20. So if I multiply that by 2, that gives me my 40. So it seems like the pattern is if I multiply each number by 2, that gives me the next number. So 40 times 2 would be 80. So my conjecture is 80. And then it says the next two terms, so then I have to do the next one after that. So 2 times 80 would be 160. So my conjecture would be 80 and 160. So I go ahead and that is indeed the answer. Okay? Let's go ahead and look at this next one here. 3, 3, 3, 3, 3, 3, 3, 3, 3, 3. So based upon what you see here, the pattern, what would be the next two terms in the sequence? Well, it looks like they're just adding another digit 3 to each one. So the next one I think would be 3, 3, 3, 3, 3, and then the one after that would be 3, 3, 3, 3, 3, 3. So I'm thinking that that's going to be what that answer would be. And actually, I know that's what it is. That answer's off to the side, so we won't do that one any further than that. Let's see. These down here, some of these you might know what they're talking about. You just don't know what the next ones are. So you may have to go online, do a little research to figure this out. But I'll tell you what these are, and you can figure them out for yourselves. So George, John, Thomas, James, these would be the names of the first presidents. So you're looking at George Washington, John Adams, Thomas Jefferson. Was he president? Yeah. Okay. James, I'm not sure, quite frankly. Ask your history teacher. But so you need the next two presidents. Here, I'll give you a hint, but I'm not going to tell you on this one. These are related to these. Okay, that's the only hint I'm going to give you. These are related to these. Clear that up there. Okay? It says use the table and inductive reasoning and then make a conjecture about each of these. Now this table right here is, you'll notice that these are even integers. Okay? The sum of the first 6 positive even numbers. Well, here's the even number 2. That's one even number. If you added it to just itself or to nothing, you'll get 2. Now another way to get that is 1 times 2. Now if you take the first 2 even numbers, 2 and 4, those are the first 2 even numbers, right? 2 plus 4 is 6. Well, I can also do 2 times 3 and get 6. If I take the next 3 even number, or just the first 3 even numbers, 2, 4, 6, if I add them together, that gives me 12. Well, I can also get 12 by doing 3 times 4. Then if I took the first 4 even numbers, 1, 2, 3, 4, and added those together, I get 20. That's 4 times 5, I get 20 as well. If I do 5 even numbers, the first 5 even numbers, 1, 2, 3, 4, 5, 2, 4, 6, 8, 10, add those together, I get 30. 30 I can also get at by doing 5 times 6 is 30. Now there's a pattern that's developing here. There's a pattern of taking this many even numbers, adding them together. I can get the same result by multiplying these two together. So you're looking for the pattern between, here's 2 even numbers added together, 2 times 3. Here's the first 3 even numbers added together is 12. That's the same as 3 times 4. The first 4 even numbers is the same as 4 times 5. So there's a pattern here, and you're to use that pattern to answer these. What you don't do, and students do it every year, but don't do it, when it says this, find the sum of the first 30 positive even numbers, I have students going out here on the side of the paper, 2 plus 4 plus 6 plus 8 plus 10 plus 12 plus 14 plus 16 plus 8, and they list the first 30 numbers, and then they add those all up. Or they just do it on their calculator, 2 plus 4 plus 6 plus 8 plus 10. That is not using inductive reasoning, and therefore that is wrong. It's not about trying to figure out what that adds up to. That's not the point of the question, okay? There's lots of ways to figure that out. Calculator, doing it by hand, whatever. So it's not about getting the answer. It's about using inductive reasoning to get the answer. And inductive reasoning is, again, using patterns. So you have to look at this table, figure out what the pattern is, and then use that pattern to make your conjecture, okay? So make sure that you're using inductive reasoning, not just trying to figure out what the sum of the first 30 even positive integers are, because that's not the point of the question. Okay, so for questions 25 through 28, and there are some other ones, it says find one counterexample to make or to show that the conjecture is false. So what we have written here is somebody has made a conjecture. They're making a statement. And you need to prove that they're false. And you can't say, well, you're wrong. Why? Because you're wrong. You can't say that. Okay, that's not proving anything. What you have to do is give an example that shows they are wrong. So for instance, the first one, the sum of 2 numbers, so you're adding 2 numbers together, is always greater than either of the numbers. In other words, this person's saying, their conjecture is this: when you take 2 numbers and you add them together, you're always going to get a number that's bigger than either of the 2 that you added together. So you have to prove that false by giving an example. So you have to give an example where you take 2 numbers, you add them together, and the answer that you get is not bigger than one of the 2 numbers. If you can do that, you've proved them false, or you prove their conjecture false. So give me an example, or can you think of an example? A couple ways to do this. I could think of maybe 5 plus 0 is what? 5. So the sum of my 2 numbers, which is 5, is bigger than either of the numbers. So is 5 bigger than 5? No. So there's a conjecture, or there's a counterexample that shows you can add 2 numbers together and not get a number that's bigger. Another example would be maybe to add a positive with a negative. So, or add 2 negatives. Okay, so negative 3 plus a negative 2, that's a negative 5. Negative 5 is actually smaller than both negative 3 and negative 2. So you need to provide an example where each one of these is incorrect.